Okay, so today we're going to be talking about number theory still, but we'll be going over the modulo arithmetic uh, part of the slides. So, so first we're going to define what is modular arithmetic, and it's basically you're looking at the remainder of something, and then all of the stuff that have like the same remainder when divided by n have like similar properties, and then you can use those properties to like do some stuff. That's a bit vague, but I'll be. Oh, wait, sorry. Oh, did I stop screen sharing? Okay. So special thanks to Dennis Chen who helped me edit this section. So here's the definition of modulo that we're going to be using. So we say that for positive integers a, b, and n, that a is congruent to b modulo n if and only if a minus b is a multiple of n. So notice that like a minus b can be a negative multiple of n, like negative n or negative 5n. So it's possible for oh shoot, it should say for integers a and b, not positive integers a and b. But n has to be positive because hold on, my Apple Pencil is not working right now. So that the positive integers thing should only describe n. A and b can be integers. So, and we say that the residue of a taken modulo n is the integer b that satisfies. So b is greater than or equal to 0, and it's less than n, and a is congruent to b modulo n. So it's b. You can think of b as the remainder when a is divided by n. And here are some exercises to so compute the residues of the following. You can just like type your answers in the chat. Oh, okay. Okay, so I got my Apple Pen. Okay, so let's go over the answer. So for the first one, it's a 4 because so when you do the division, you get a remainder of 4 at the end. And okay, and for 9 factorial, you have to think a bit about the definition of 9 factorial. It's 1 times 2 dot dot all the way up to 9. And since there's a 7 in here already, you know it's divisible by 7, so it's going to be 0 mod 7. And here, you could also you also need to do a bit of thinking. So this is actually well 10,000 minus 9, which is 100 squared minus 3 squared, and we use difference of squares on this to get 97,103, which is obviously 0 mod 7. Oh, okay, it's going off the page, but yeah. Okay, now which of the following are true? Right, so we're going to go back to the definition of like of what it means to be congruent modulo something. So again, remember that the definitions take the difference of the two numbers and see if it's divisible by the modulo. So the difference of 5 and -1, so the difference here would be 6, which is a multiple of 6. So it is true. And here, the difference would be and here we have difference of squares again. It's going to end up like this, which is free. Okay. And now we're going to go for some of the properties that these numbers have, like, so you can actually manipulate them pretty easily. So let the sum of the digits of a number n be s of n, then s of n is congruent to n modulo 9. So, and a corollary of this is if you define s of n as before, then s of n is congruent to n modulo 3. So this is very useful for quickly evaluating a number when you modulo 9 or 3. So what you're going to do is you're going to like for example, oh shoot. Okay, this is weird. My Apple Pencil is not working again. But for example, if you wanted to compute like the 1001 like if you want to test if 1001 is divisible by like 3, you just add the digits, which is 1 plus 1 equals 2, and 2 is obviously not a multiple of 3. So yeah, you can test if stuff is divisible by 3 and it's like residue when divided by 3 pretty easily. And here's a similar formula, but it's for modulo 11. So, and there's actually a reason. There's a really nice way to memorize this once you see the proof. It becomes like way more obvious why this is true. Uh, oh, okay, my pencil's apparently no. Hold on a second. I need to try fix my pencil. Okay. I'm okay, let's go. So I'm going to let you guys have about a few seconds to look at this formula and really understand what it's saying. So basically you start at the very right and then you alternate the sign of the digit like as you go over all of them. So like you start with positive, then negative, then positive, then negative, and you do that until you hit the end of the number. And so here are some exercises. Okay, and again, just like submit your answers in the chat box. Okay, so yeah. Uh, okay, so okay, the first one is just the numbers 1, 2, 3, 4, dot, dot, 4, 2, 42, 43, 44, concatenated in like series. Like they're so okay. I could have defined this more explicitly, uh, but I wanted to save some space. So it should so it's yeah, it's if you expand it out more, it should be 1, 2, 3, 4, 5, 6, 7, 8, 9, 1, 0, 1, 1, and so on. Okay, yeah, so Lily got the right answer. Yeah, so it's 1 plus. So what you need to do here is you actually need to apply the sum of digits rule twice. So the first time you're going to get let's see if okay, yeah, it does work. Just okay, so what you're going to get the first time is you're going to get 1 plus 2, 1 plus 2 plus 3 dot dot plus 44 plus 2 plus 4 plus 3. And then at the end, you're going to recombine them into like their original numbers. Okay. Uh, okay. It's my Apple Pen's again not working. Okay, this is sad, uh, but okay, at the end, it's 1 plus 2 plus 3 dot dot plus 42 plus 43 plus 44. And then you use the arithmetic series formula, which is so it's going to end up being 44 times 45 divided by 2, which is 22 times 45. And since 45 is 9 times 5, it's going to be a multiple of 9, so it's going to be 0 modulo 9. Okay. Hopefully it's going to be working by the time I get to the problem section. So here's so basically you can add stuff in modulo n, and the residues are also going to be added, and then you take the residue of the sum of the residues, and it's going to be the residue of a plus b. Hopefully, okay, that might have not made sense, but looking at the formulas, you can see how that's intuitively true, right? Okay, so and here's an easy exercise that's yeah, okay, so yeah, it's -1 or 8. So so again, we use the sum of digits formula from before. So and you get 35, I believe, from just like adding up all of the digits. And yeah, so, and that's like -1 modulo 9 or 8 modulo 8 modulo 9. Okay. Okay, so, and what this says is you can multiply modulo n, and it's like this, like if a is congruent to x modulo 9 and b is congruent to y modulo n, ab is congruent to xy modulo n. And the proof is kind of messy, but it's like, yeah, it's, yeah, you can see how it's like basically the stuff that's not divisible by n immediately cancels out, and at the end you have like something that's a multiple of n. Oh, and I don't know if this is like uh obvious to you guys, but like if two numbers are congruent modulo n, then they have the same residue. Okay, I'll write that down somewhere, hopefully. Okay. Uh, yeah, if, shoot, okay, my R945 is going to work that time. But, okay, so here's another exercise. Yeah, so it's 2. So the way that you're like kind of supposed to use is just like find 2010 modulo 7, and you like do the division here, but because like because it's kind of a pain, you can also just memorize that 2016 is a multiple of 7. Yeah, so, and then you just like subtract 7 to get 2009 is 0 modulo 7, so 2010 is 1 modulo 7, and get 2032 is like 2 modulo 7. Okay, so okay. And yeah, so notice that we implicitly use the property from before, because so we got that like 2032's 2 modulo 7 and 2010's 1 -1, wait, yeah, 1 modulo 7, and you multiply these two residues together and you got 2, which is going to be the residue of the whole entire like product. And here's yeah, so yeah, so here for integer ab and positive integers nk, if a is congruent to b modulo n, then a to the power of k is congruent to b to the power of k modulo n. And the proof is just like, yeah, it's just this. Okay, some new people joined right now, which is kind of sad because I've just gone. Okay, because this is a subject that builds on itself quite often, so I'm going to go back to the very definition quickly, so they have an idea what's going on. Because otherwise it's going to be okay. Okay, so here's the definition for who, like, the people who just joined right now. And you should take note of the footnote that they're congruent modulo n and not equal modulo n. I didn't point this out the first time, so okay, and here's the definition of a modular residue. So it's basically the same as the remainder. And okay, okay, and I'm going to go on to more advanced properties now. Basically, addition and subtraction and multiplication and exponentiation like kind of work the same way. Like if you have two numbers are equal, then when you put them to the same power, then they're going to be equal. And like if you subtract them, the residues are going to be subtracted too. Okay, so here's the first advanced property that we're going to look at. So for integer AB and positive integer n, we say that AB are inverses of each other if A times B is congruent to 1 modulo n. Okay, so the reason why this is useful is because it actually comes up quite often when you're trying to look at like some equation, and this equation's like equal to like 0 modulo something, and then you can like rearrange the equation to get that like if you determine all of the variables except one of them, then you have that the remaining variables like already determined because of this next thing that okay I didn't include the properties, the existence of the inverse in here for some reason, but basically if A is okay, so if A is relatively prime to n, so we have the inverse exists for like these A. Yeah, so and remember 1 over A is just means the inverse of A. And here's some stuff that you have. So it's like the same as fractions basically. Like it's literally just like fractions. So yeah. I'm not going to make you guys prove this because we need to move on. Oh, and I did include the existence of inverses, except yeah. Right. So the proof has actually gone off the page. But like it's on the handout. So if you guys are interested in the proof, you can just like read it. There, the uh, the idea behind it is that when you multiply by like some integer k, then uh, well, okay, so yeah, so if you look at a to a3 a and dot dot n minus 1 a, which is the same as like multiplying each residue by a, then this is just a rearrangement of 1 2 3 dot dot n minus 1. And from there, it's like one of the terms have to match up, right? Because like one of the terms has to match up to 1 because it's a rearrangement. That's like how rearrangements work. So that term that matches up to 1, that corresponds to the inverse of a, like the definition. Okay, and here's this is actually what I was talking about before. This is kind of a classical example of why inverses are useful, like even for the AMCs and like Amy. This isn't going. By the way, I don't know if I said this before, but uh, modular arithmetic, it doesn't really show up on the AMC 8, but it does. It like it's pretty much off the number theory on the AMCs, like AMC 10 to AMC 12s and Amy. So yeah, so like this is basically AMC 10 prep. But if you know all of this, then you're going to be super prepared for the AMC 8 because there's like no way they're going to make anything harder than the stuff that we covered here on the AMC 8. So anyways, I'm going to give like 15 seconds to read this because I'm going to be going over the solution. Okay, so here's a walkthrough of the solution. So our first step is we need to rewrite this in terms of modular arithmetic, which is a minus b minus c. Oh wow, my pencil's working now. This is amazing. Okay. Okay, so if we determine d modulo 5, then how many possible values of d are there? So, and okay, the obvious answer is like 1 because like d, so if like d equals 1 mod 5, then it has to be d equals 1, right? And that's like, yeah, because like if you 6 and like -4 are out of the bounds. So if we determine ABC, then do we determine D? Yes we do. Because, okay, look at this. So we can rewrite it to be AB equals CD mod 5. So this means D equals AB over C mod 5. Right, if we determine A, B, and C, we can just like evaluate it and like we use the existence of inverses here. Right. So, and how many possible ABC are there? So, okay, and this is just 4 to the power of 3 because you can, there's 4 values for A, B, and C. Right, so our answer is 64 in the end. Okay, now here's a, okay, so this so the Chinese remainder theorem is states that if you have like n equals p1 to the power of q1 times p2 to the power of q2 and so on for primes like p1, p2, dot dot dot, then if you determine k is equivalent to is congruent to a modulo that so basically if you determine k is congruent to a for all of these, then you have k is congruent to a, wait, okay, this isn't actually the statement of Chinese remainder theorem. Wait, actually it is, yeah, it is the equivalent. But like here's a restatement that's like more popular than this like statement. So if you have, it's like, shoot, my, no, oh, okay, good, my pencil's working still. So if you have that, it's R1 like mod P1 Q1 mod frick R2 mod P2 Q2 and dot 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 and so on, then you determine R mod N, like, okay, so basically if you find out its residue modulo like its prime factors or like the power of its prime factors, then you can determine the residue then you can determine the residue mod itself. Right, so, and the like text below it states what you want to do. So say you want to find n mod n, then you can break up finding n mod n into finding n mod p1 to the power of q1 and so on, and then at the end you can find mod n again. So how this looks like is so say you want to find mod 100, frick, then you, okay, I was going to write that out, but again, it's not working. So say you want to find mod 100, then you find mod 4, and you find mod 25, because 100 is 2 squared times 5 squared. And, like, if you want to find mod 100 and, like, 20, then you find mod 4, mod 5, well, you find mod 8 actually, 8, mod 5, and then you find mod 3, because 120 is 2 to the power of 3 times 3 times 5. And yeah, so it's kind of not useful by itself, but basically it's saying that you can do this and you're going to be correct at the end when you like find mod n. Also, I just realized that it's probably not a good idea to make one of the variables uppercase n and one of the variables lowercase n. That's confusing when you say it out loud. And here's like what I recommend you to do when you're working with mods. So, and yeah, you can read it. I'm going to give you guys about half a, or actually like 1 minute to read it. Okay, so if you guys are done reading, so uh, I'm going to just go ahead. Oh, and by the way, when it says like the primes are either 1 or -1, that's referring to the residue, like modulo 4, modulo 2, 3, or 4. So here's our first problem. It's okay, this is actually going to be like the hardest. This is going to be like train 5 on an AMC 8, but uh, but like it's probably going to be very easy on an AMC 10. Like it's going to be like 10 or like 10 to 14. Right, and remember like the thing I just talked about. So if like the modulo is composite, then break it up into like prime factors. Like you literally just find the number modulo its prime factors. It's and uh, I haven't like described to you how you would actually like get the like modulo n back at the end, but yeah, I'm going to show it to you like I guess on this problem. Okay, actually, I'm going to stop screen sharing for a bit because I'm going to actually try to find out what's wrong with my Apple Pen because I know it's fully charged, but it's like not working still. So I'm going to type out the problem in chat if like you don't like remember. Okay, apparently, okay, this is actually pretty wacky. My Apple Pencil immediately started working when I stopped screen sharing. So, yeah, that's kind of okay. I don't actually know what's happening now. Okay, I'm going to start. Okay, I'm going to present the solution. Uh, yeah, I think it's yeah, it is free, modulo 15. So our first step is apply CRT. So we want to find a mod 3 and mod 5. And when this, like, call this number n, because I don't want to write out a ton of digits. So n mod 3 is, so we use the sum of digits, a property that we talked about before. You take the sum of the digits and you take that residue, take the sum of the digits mod 3, and that's equal to the number itself mod 3. So we have that this is what's equal to, right? And that's like 2018 times. Now, uh, we can apply the sum of digits stuff again on 2018 to get. Yeah, so, and then you just like, wait, hold up. Okay, okay, guess it's not actually mod 0 mod 3. It's 1 mod 3. And n mod 5. Oh, I didn't go for this property, but like it's kind of obvious. So the last digit mod 5 is equal to number mod 5, right? Because like the other digits are going to be multiplied by 10 and stuff. So it's not going to like contribute anything to the number mod 5. So it's going to be 8 mod 5, which is 3. And then so we have that the number is 1 mod 3 and 3 mod 5. So 1 plus 3. So like, so it's going to be something in the form this. And then you have this, and then you take this modulo 3 again. Okay, yeah, so that's like pretty clear, right? Like you can see steps that lead logically from here, right? And then you have y equals 2, because okay, so I should have said this before, but okay, this is actually n mod 15. Yeah. So, and so like n's going, so n mod 15 is between 14 and 0. So y is going to be 0, 1, 2, or 2. So y equals 2 is the only thing that works here. And you get n equals 13 mod 15. So find a number of positive integers x less than 100 such that this big thing is a prime number. And so one thing that should be kind of obvious to you is that it's like impossible to like test like x equals 10 or like x equals 15 to see if it's prime, because it's going to be huge. It's going to be, you're not going to be able to do it. Also, just like too many numbers to check. And typically in these kind of problems, when it asks you to do some like impossible task, the solution is that again the like there it's impossible. You're not it's so like it's going to be 0 typically. It's not going to be possible to find a positive integer x such that this is prime. And the reason for this is so again, like when you're looking at primes, you take it 2, 3, or 6. Yeah, 2, 3, or 6 typically. And if we take a mod 3, because like if we take a mod 2, then it's like odd plus odd plus odd plus odd plus odd plus odd. Well, okay, there's like 7 odds, so that's an odd again, and that's like not bad. Primes can be odd. All of them are odd, actually, except for 1. So it's not good. But if you take a mod 3, okay, again, okay, my pen's not working. This is okay. Okay, it's working now. So if you take a mod 3, right? So if x equals 0 mod 2, then you have this is equal to 1 plus 1. Frick. Okay. Yeah, so in both of these cases, it's going to be 0 mod 3. And because it's 0 mod 3, it's not going to be a prime, right? Because it's going to be greater than 3 and not in 0 mod 3. Right, so the answer is a big fat 0. Okay, and here we're going to use Chinese remainder theorem again. Actually, I'm going to let you guys have like 2 minutes to see if you can figure it out by yourselves. So here's a hint. Uh, so a so a cubed is congruent to a mod 2, right? Now, can you say the same thing about mod 3? Like, is this actually true? And the answer is kind of obviously yes, it is true. Because 0 equals 0, 1 equals 1, 8 equals 2. Right, so, and then you have and this is 2 actually 2 train 18 mod 6. Okay, okay. Okay, yeah, sorry about that. So we have that this is like, can you guys see the bottom of the screen? Uh oh shoot, that's unfortunate because I wrote all of my work at the bottom of the screen. Okay, so here's a recap. So, and you can check this kind of easily, but it's like pretty well known. Like, so you should just like memorize it. So, and then you have like the thing here. And so we apply Chinese remainder theorem again. Yeah, so it's gonna be 4 mod 6. Right, so like, do you guys understand like each step of this, like how each step works, basically? Because like, we're actually using quite a lot of the stuff that we talked about before in like a single problem here. So like, you kind of need to understand all of the stuff we covered pretty well in order to understand like this like solution. Okay, so I'm going to be moving on. Okay, and I think this one's actually more reasonable. It's pretty easy actually. Yeah, so it's -2 or 27. But like you should actually reply with 27 because again, even though it is like -2 modulo 29, the remainder is going to be positive always. So like that's kind of the difference between mods and remainder is mods can be negative, but remainders can't be negative. So like keep that in mind. So you have 4 to the power of 14 minus 1 equals is congruent to 0 mod 29. So you have this is right, and you have that these two numbers here. So these two numbers are relatively prime because like their odds separate by 2, and like yeah, it should be kind of obvious why. Well, okay, and well, actually, the main thing you need to keep in mind is you don't actually need to know they're relatively prime actually, but they're it's impossible for both of them to be 0 mod 29, right? Because like if they were both 0 mod 29, then that would imply that 2 is congruent to 2 mod 29, which is like impossible. And we're given that 2 to power of 14 minus 1 is not equal to 0 mod 29. So we have that like the other number is equal to 0 mod 29 and 2 to, and again it's just like subtracting 2. Yeah, so and then we get this. Okay, here's another problem that's kind of difficult. We're actually, so if you look at the top, we're actually reaching the harder problems now. We were on the easy problems. But like this is kind of relative to like the AMC 10 level. So like if you can't exactly, like if these seem pretty hard, it's probably because you don't have like that much experience with mods yet. The best way to get good at mods is just to do a lot of problems. Okay, so I'm going to present the solution now. So, like the first thing to notice here is that 14 is 12 squared, and these two numbers here are like 12 plus 1 and 12 minus 1. So like you don't want to use so you don't want to use CRT because you have a special modulus. So when you have like 12 plus 1 20 plus 12 minus 1 20, you have this is so okay sure, I don't know if I taught you the binomial theorem yet, but if you apply that, then you have this is equal to 12 20 but minus plus 20 choosing choose one, and wait, hold on, I'm going to actually reformat this because it's kind of hard to like write this out sequentially. So and this is going to be equal to 20 times 12 plus 1 mod 12 squared, right? Because and similarly, this is going to be equal to negative 20 times 12 plus 1 mod 12 squared. And when you add these together, these negative 20 times 12 and these 20 times 12 cancel out, so you get okay. Yeah, so yeah, I should have actually gone over the binomial theorem before I did this with you guys. Uh, okay, this one should be more durable. It's so like I said, when you can use mod 9 and mod 3 to get information about uh like the digits, like so if you know what the number is mod 9 but you don't know like the digits, then you can like use the fact that's like 0 mod 9 to find out information about the digits and like go from there. Okay. Okay, yeah, I'm going to present the solution now. So the first step is kind of to use the hint that I gave you before. Uh, so look at mod 9. So 19 factorial is obviously 0 mod 9. So, and then you have, if you look at the sum of the digits, then you will get that, I think 33 plus t plus m plus h equals 0 mod 9. Wait, uh, hold on, let me check my adding. Yeah, so t plus m plus h equals 3 mod 9. Right, because like the sum of this is 4, sum of this is 11 plus t. Sum of all of this is just 1. So in the end, it's going to be, yeah, it's, okay, I think I did it correctly. But then you have, so here's the second step. Notice that h equals 0. And the reason for this is because 19 factorial has so it has 3 factors of 5, right? So it has 3 factors of 10 because the number of factors of 2 obviously outnumbers the number of factors of 5 when you're like multiplying everything from 1 through 19, right? So what we're left with is actually t plus m equals 3 mod 9. Now, so what we have is t plus m equals 3, or it's equal to 12. It can't be equal to like 21 because remember t m is less than 9. So we need one more bit of information and we're kind of done. Now we're going to use mod 11 now because like remember we have that the alternate sum of the digits is equal to the number mod 11. So the alternating sum is going to be something like this. It's right. So you get m minus t equals 3 mod 11. And now what does that mean? So consider if m plus t equals 3, then possible m would be 0, 3. That's the only possible m and t. So Well, if you have n plus 2 equals 12, then right, so if you have n plus equals 12, then you can find that that only two, wait, yeah, 210 works here, which is like, yeah, yeah, I'm pretty sure that's, yeah, okay. Yeah, so like if you have n plus equals 12, then you have like 210. And like that's impossible because t can't be 10 since it's like a digit. So, yeah. Right. Also remember that like these numbers are digits, so you have like some bounds on them. Right. Yeah. Okay. Yeah, I think that's like the solution. Okay, might be. Okay, yeah. Unless I, unless I did some stupid adding mistake, that's correct. Oh, and this one's kind of more fun. We actually need to end soon, so I'm going to go for the solution very quickly right now. So it's kind of just like testing out the terms of this sequence. Like you just right, and here notice that we've basically gotten back to where we were at the beginning, except it's times 3. And the thing here is like intuitively everything's going to be uh like times 3 from here on. And when we go further, we're going to find wait, yeah, so this is right. So what we have here is that we now can conclude that f 5n, yeah, f5n equals 3n. So actually 5, yeah, so and then we have f2017 equals 2 times so it's 2 times 3 to the power 403. And here's, and then again we look at patterns among 3 to the power of x. This goes 1, 3, 9. Actually, we can rewrite 9 as -1, -3, negative. Oh, and we have 1. So it repeats every 4 numbers. So 3 to the power 4 equals 3, 0, and so, and then we have 3 to the power 403 equals 3, 3. 3 to the power 3, which is 2 mod 5. And then going back to here, we have this is 2 times 2 equals 4 mod 5. Okay, and that's, yeah, so times, yeah, so class is ending now. It's already 2:10:48. So, yeah, I'll post the recording of this on the Google Classroom. I'll also post the slides and handout. So, bye guys.